Okay. So today I'm going to be presenting on 60 years of archaeomagnetism in the United States. And this is kind of a fun month for archaeomagnetism because the first samples were collected 60 years ago in the month of March. And so that's really fun for us. All of these samples that have been collected, with the exception of a random few percent that we can't find, are now located here in this building. So everything that I will be talking about today in terms of sampling and data, the physical samples, the field notes, all of the metadata, digital and printed, are currently in boxes in the Archaeomag lab. Since there are so few of you and most of you have been here before, we can walk down and look at those when we're done. But everything is in boxes because we're working on actually creating an archive where these data that I'll be presenting today can be utilized by the scientific community. So we have a lot of different projects going on. Thanks, Melissa. And this is more of an overview of what archaeomagnetism is. So Earth's magnetic field is really critical to life on Earth. Without Earth's magnetic field, it has been postulated that we would actually not have life on Earth. And this is because Earth's magnetic field actually acts as a barrier and a filter for the charged particles coming in from the sun in the atmosphere and the interstellar regions in the form of solar wind. It hits Earth's magnetic field because the particles are charged, and there's this relationship between electricity and magnetism. It actually effectively shields and filters the amount of harmful radiation coming from the sun and hitting the surface of the Earth. So from a basic biological level, super, super important. We have a ton of studies now that are starting to come out that show how important Earth's magnetic field is for the biological processes on Earth and how animals, we're considered an animal too in this case, actually respond to Earth's magnetic field. So bacteria, sea turtles, things like that. And because of the shielding power, it actually mitigates the space weather and protects our technology. Because our technology is also based in electricity and radio waves and a whole bunch of other different types of electromagnetic signatures, our Earth's magnetic field effectively shields and protects these as well. If we were not to have Earth's magnetic field, our technology would look wildly different. And if something were to happen to Earth's magnetic field, our technology would have to adapt really, really quickly, because we'd have so much impact from the space weather coming in, and it would actually cause a ton of noise on our electric lines and things like that. I did not really get to experience this, mostly because television was not a thing when I was growing up, but when you get to those staticky channels, that is the noise that is making it through these filters of Earth's magnetic field. And that is coming in from the interstellar regions, primarily our sun. Through time, Earth's magnetic field has been used for navigation. The map I just put up on the screen, you'll see in a little bit bigger version in a couple slides. But this is the first map that shows Earth's magnetic declination ever made. And this was made from a whole bunch of ship records, captain's records, expedition records that were collected in the 1500s and 1600s. And then they were compiled into this map in 1701. And what you can see here in the middle of this is the line of zero declination. So if you were to go out and remember your scouting, Boy Scouts and Girl Scouts from when you were little, you would have to set your compass to a magnetic declination in order to actually navigate around. This is the first map that actually defines what that looks like. So this line is zero declination, and then to the west of it, this line is positive, and to the east is negative declination. And that has since changed. And that's a lot of what I study, is the change in these type of maps. And then going back to our sea turtles, because they're fun, not only do humans use tools to allow us to navigate, but other animals like sea turtles, whales, birds, bats, bees. There's been studies on cows. Those actually didn't come up with anything useful. but there's a ton of animals that do sense Earth's magnetic field and use Earth's magnetic field to navigate. The most obvious example is bacteria, because they're easy to work on in a lab, and you can have a petri dish of bacteria and have a magnetic field, and then you can switch it. And the petri dish of bacteria, the little bacteria move back and forth, and it's really fun to watch. You can't really see that with the naked eye, but it is fun in a scientific petri dish to look at the bacteria's move. But you can also use Earth's magnetic field and Earth's magnetism as a tool. So on the screen, I have a couple of examples. Earth's magnetic field and understanding Earth's magnetic field was critical to the development of plate tectonics and the acceptance of plate tectonics. And it also helps us understand how old the seafloor is. So all of these different colors that you see here have been, in many cases, confirmed with argon or dates from deep sea collection expeditions. But for the most part, all the different colors you see that map the different ages of the seafloor, young in red, grading to blue, and then pink in our absolutely oldest sections, all of that is coming from magnetism. And we have a ton of different shipboard records that drag magnetometers behind them, and then we can put together these maps. And we can actually see fault lines and where some of the plate boundaries are using magnetism. Also, for plate boundaries, we use earthquakes and volcanoes, but there's a lot going into this map behind the scenes, and a lot of it is coming from the field of paleomagnetism. On land, we can also do the same thing with chronology, and here in New Mexico, this is actually wildly important. During the 1960s, we had the space race, but there was also this geomagnetic timescale race that nobody has ever heard of. Most people have never heard of the geomagnetic timescale either. But it's the timescale that is allowing us to create these maps over here. We can do the same on Earth, and we can look at the polarities of rocks, whether the North Pole was in its current configuration, normal polarity like today, or whether it's in a reversed polarity as it has been in the past. And during the 1960s, they were trying to find examples of rocks on Earth that had reversed polarities. And they did, and they found them right up here in our mountains in the Jaramillo Creek of the Jemez caldera. And so now we actually have a time period in the geomagnetic timescale named Jaramillo after that creek, which is kind of fun. And that is the segment that is actually critical to human evolution and being used in like Olduvai in Ethiopia for dating out there. We also can do mining and geology with magnetism. So that's an example over here. This is aeromagnetism with drone footage or drone data from a magnetometer attached to a drone. And this is looking at a wildly complex set of geologic terrains in Europe, and they're trying to understand the history of the geology here. It's an accretionary system. It's wildly complicated. There's a ton of mining going on. And so they've been using aeromag and electromagnetism to try to understand where the best sources of magnetism or of minerals are based on their magnetism. They also use gravity and a whole bunch of other things in discrete sampling, but it's a fun, colorful image just to show that there's a ton of diversity here. And then a super fun one is we can actually use magnetometers on satellites to study not only Earth's magnetic field, we are swarming with magnetometers around us, but also not Earth. So we have examples here. This one is of Neptune, and we can see the field of Neptune. This is an old image. It's actually been upgraded a little bit. But you can use the magnetic field of not just Earth, but these other planets to try to understand what is occurring inside the planets. And this is our only real way of understanding what is going on and the inner dynamics of some of these planets that are not Earth, because we can't get there ourselves. They also use gravity, but gravity and magnetism work hand in hand. They both produce images like this, and we are using them all the time. So that's kind of what magnetism is, why it's important today, and what it can study as a tool. But how do we actually go about doing that? And as I mentioned, we can use satellites. This is only the last 60 years, really. So if you want to go beyond 60 years and get additional data, you'll have to go to our magnetic observatories. These, by the way, are continuously on the chopping block for funding worldwide. So advocate for them. But you can only get about 200 years in the past with magnetic observatories. If you want to go even further back, you can use these expedition logs, which is how Halley had produced this original map of Earth's declination. And if you want to go even further in the past, that's when we get to archaeomagnetism and paleomagnetism. And for archaeomagnetism, the definition that I used is that it is magnetism of archaeological sites that have an anthropogenic influence. So that could be dirt, that could be rocks. It doesn't matter as long as they're influenced by humans. And that is capped at a couple thousand years, mostly because, yes, we can study magnetism going back at any time period, but we don't have the same chronological control that we do in the more recent thousands of years. And if you want to study rocks, that's the field of paleomagnetism. Rocks are actively being produced today, and they are 3-point-something billion years old if you talk to certain laboratories. And so that's the field of paleomagnetism related to rocks. So how do we actually study this? I wish that rocks would just tell us or have it inscribed into the rock. This is not the case, obviously. And so we have to look at the little tiny magnetic vectors. This has a basis in physics, and the ideas that underlie this video that I'm going to show you have their foundations in the 1700s. And were really studied in the 1950s, 60s, and tons of papers are still coming out today. So what I'm showing is the cooling of a magma chamber, and the little grains are crystals that will start to form. Not every crystal in a magma chamber or a rock has a magnetization. So you will see that not every crystal in this depiction will have a magnetization. When magnets are really, really hot, they lose their magnetization because they have a thermal expansion that actually breaks down the coupling between electrons that is required to keep a magnetization. And so that's what you'll see is these magnetic little lines are going to be bouncing back and forth because they're so hot.
Can you force that to happen?
You can, and that's actually how we study these things. Can you artificially make this happen in a lab? And the answer is yes. So as the temperature is cooling, you can start to see that the magnetization, which is the little red lines, start to bounce a little less quickly, and then they eventually get locked in place. And this is the fundamental theory behind magnetism. If they didn't get locked in place, I would have no job. Flat out. They have to be locked in place. And paleomagnetists are not creative with their naming. So this is the blocking temperature. They get locked in place at the blocking temperature. Not very creative. And if we were to heat them back up in the lab, then they'd unblock at the unblocking temperature. So I'm going to play this again. And the reason I start with a magma chamber, which is obviously not what I study here, is because it's pretty simple to kind of understand. A magma chamber is hot and then it gets cold. That's what they do. When we're studying paleomagnetism, or when we're studying archaeomagnetism, you can have a much more complicated heating history. And so come on, slide. So in archaeomagnetism, we study things that have been burned, taking advantage of the relationship between heat and magnetism. Once something cools for the last time, its magnetic properties get locked in place, and they do not move. They do not change. That is what they are until they're heated again, or in the case of pottery, until we pick them up and move them out of the kiln. Then their orientations get changed a little bit, but that's because the whole pot is moving around, not the little tiny grains within the pot. So what I'm showing here is an example of kind of the range of things that get burned in an archaeological context. So it can have earthen structures, we can have floors, fire pits or hearths, You can have kiln pits, pottery, or burned adobe or daub, depending on where you study. That word is kind of used interchangeably. In all of these cases, the big component of this is that they are heated. So how does this work in an archaeological context, not a magma chamber? I don't have a cool video for this, so you'll have to bear with me with my little comic strips over here. So we have a prevailing magnetic field on Earth. This is Earth's magnetic field, but in a laboratory, you can force this to be any direction you want. You make your pot. All of the grains are just coming from wherever you're grabbing your grains from to make your pot. So they're going to have their own magnetizations that are randomized, is the assumption. Then you heat it up in a fire, and the thermal expansion of the minerals allows the magnetizations to break down, and they kind of do their own thing, like we saw in the early part of that magma chamber video. And then when it cools back down, they will do their absolute best to be parallel with Earth's prevailing magnetic field. It is never this pretty. I'm just a bad comic artist. So it is a net magnetization that is parallel to Earth's magnetic field. But I am not a good artist. I might need help from folks in this room, and then it would actually be more akin to reality. We call this a thermal remnant magnetization. And here on Earth, these can last billions of years. They do not change. If I were to take these rocks to Venus, for example, the temperatures on Venus, these thermal remnant magnetizations only last sometimes a couple of minutes because it is so much hotter on Venus during the day.
Right.
So the fact that we have thermal remnant magnetizations and we can study plate tectonics and we can study the age of the seafloor and the creeks in our area and things like that is directly related to the fact that it is cool here on Earth. So if we go into a little bit of the magnetic theory and how we actually do this, because that's a lot of like, good, let's go collect some samples. What does that look like?
Right.
Here I have an example of one of our sample cubes adhered with epoxy to a rock that was in an archaeological context, and we were trying to understand its magnetic characterization and its magnetic direction. So I have, again, I'm not a great artist, put a couple of little magnets, compasses, magnetic grains into this schematic. And I have attached my cube to my rock. The cube has this little curve on it, and that is really critical to helping me understand how this rock is oriented in space. So what is its geometry with respect to Earth's current magnetic field? And that value is preserved throughout the entire experiment. The sample can move around, that's no big deal, but because I have this reference corner, I know exactly how this cube and this rock were oriented in the archaeological site. Inside this sample, there are bits of rock, effectively, because this is a rock. This could be burned dirt or anything that I am sampling. Because of the magnetometers that we have here that actually spin the samples, I cannot just have loose dirt floating around. It will make a mess. So we completely encase the sample in plaster. And what that looks like is I actually cut this rock and have a little bit of the rock remaining on the bottom of this cube. I re-encase it, so now it's more of a rectangular prism and not a cube. And then I cut off the end to make it a cube. And now I have a cube with burned material inside the cube carrying its own magnetic vector. We refer to those vectors in declination and inclination. And this is kind of like your polar coordinates that you learned about in algebra. So you have your Cartesian XYZ, and then you have your polar coordinates. It's effectively the same thing. A lot of the math is the same behind the scenes. And then I study them. And then the magnetic vectors that are preserved in my cube with the orientation corner allow me to plot what Earth's magnetic field was doing at the time that the sample cooled in the past. It's like a little photograph. So I might get an image like this of 4 different photographs around the world. You can't do anything with 4. You have to have an n greater than 4. So we have gone around, and scientists around the world have collected samples from rocks, from archaeomagnetic samples. worldwide for about 50 years now. In the case of archaeomagnetism in the US, 60 years. And those samples are being preserved in different institutions around the world, and their data is being preserved in different federally and internationally supported databases. Inside Earth, we model Earth as a little bar magnet. It's not a perfect model, but it is close. And that allows us to actually do a bunch of math to make pretty models using all of those data that have been preserved in those databases. So here's an example of Earth's magnetic field declinations. So this is a moving video that is the update to that 1701 picture of the map that I showed you. And so what we're looking at is clearly Earth here, and we're looking down on the North Pole here. You can see Greenland right here. And so what we're going to watch is how Earth's magnetic field moves around in this model. And this model is known as paleosecular variation. So we're looking at the variation of the past field. It does not move around very quickly for the most part. And this is a pretty standard rate. There have been times that Earth's magnetic field does move around really quickly, and you will start to see that now as we get into the late 1800s and 1900s, specifically looking over here. So we're going to look at where our modeled North Pole is as we go into the most recent century, and it starts to move quite rapidly. This actually triggered a bunch of public articles and public newspapers and things like that a couple years ago, because everyone was panicking because Earth's magnetic field was changing really, really quickly. If you look at the last 400 years, that's true. If you use models of the past, this is normal. It's just not normal since we've started being able to really study it using shipboard records, captain's records, expedition records, satellites, and magnetic observatories. How we actually look at these data in a two-dimensional way and not a 3- or 4-dimensional way, depending on how you calculate that, is with a flat image. And what this image is doing, it's actually tracing the location of this modeled magnetic North Pole as it moves around. The way that this is described to undergrads studying this is, imagine a drunk guy holding the North Pole and walking around.
Okay.
That is about as much as we know. You cannot predict drunk people's movements, and that is the same thing in Earth's magnetic field. It is actually, all of these models are stochastic. They are based on data that we have, and they are not able to predict very far into the future because of the fact that we still don't actually know what is triggering all of the movements of Earth's magnetic field. What is that mechanism deep inside the Earth? This is an active area of study. We believe and trust that it has to do with convection currents within the outer core. However, there are also magnetic fields in the mantle and in our crust of the Earth, and their magnetic field can be affected by the solar magnetic field and other things going on.
It is so, okay.
So it's wildly complicated, and Earth's magnetic field changes on the order of hundreds of millions of years and a couple of seconds. So if you've ever been down to the Roswell Alien Museum, which is probably the worst museum I have ever been to, but is wildly entertaining, and I highly recommend you go. They have a whole exhibit on how, oh, the aliens only come at night because look at Earth's magnetic field. They clearly don't actually study Earth's magnetic field. That has nothing to do with aliens. That is just part of Earth's magnetic field. It changes on a day-to-night schedule as well because of the influence of the sun. But if we are looking at Earth's magnetic field and how it changes in the last 2,000 years, this is oftentimes what you will see. You will see a map of a VGP, which is a virtual geomagnetic pole position. It is a modeled magnetic North Pole and how it moves around. That is effectively the short story. However, it gets really complicated really quickly because you can have time periods where it loops around itself. And so we have a loop over here at the 800s and a loop over here at about the 11 to 12 to 1400s, depending on which model you look at. And this causes difficulties in using some of these curves for dating, because if you have a sample on the very edges of the curve, great, you can kind of know how old it is. But if you have a sample right at one of these intersection points where the magnetic vector preserved in the sample produces a effective photograph, this VGP photograph that plots right at this intersection point, well, it could be like 950 or it could be 750. And over here, it can get even more complicated in the like 11 to 1400s. So Earth's magnetic field has a lot of applications, even in archaeology, but it still can have its limitations. So what does the database actually look like? Well, if you were to look at the database in 2013, this is what you would see. This is a histogram showing all of these samples that were collected archaeomagnetically. So the last 2000 years is about the cutoff that I used. I used a different one in the area around China because they can go back further, and same with the Mediterranean. But roughly 2,000 to 3,000 years. The coloring behind the histograms shows the data density. The histograms shows the age of the sample being studied in the published data set. And you can see there's been a lot of work in the Mediterranean. Not surprising. There's a lot of archaeologists that do work in the Mediterranean. You can see that there is some work in the Americas and some work in China. Also not surprising. There's a lot of archaeology in these areas. The total in this database was 4,370 samples. That's it. And a sample in this case is a fire pit. So 4,370 fire pits that were studied worldwide for archaeomagnetism. Of those, only 402 published results were coming from the Americas, most of which was Arizona. This is a massive problem, as you can kind of see from this image. If you're trying to make a model of Earth's magnetic field, there's a lot of areas that have not been studied at all. And the areas that have been studied, it is primarily focused on Europe. So how do you make a temporally accurate and a spatially accurate model when your data is highly concentrated in one location? So the majority of my PhD thesis was rectifying this image for the Americas. And I was able to do that because we have 51,000 specimens of data from the Americas, and that represents 5,700 sites or fire pits. So the database before I started this had a total of 4,300, and only 400 of those were from the Americas. I added over 5,000 new data points to this database.
Good going, kid.
What do those look like? I kind of gave an example in my really terrible graphic design of a comic strip, but they are cubes with burned dirt inside of the cubes, capped. We have two different size cubes. That's what you can see here. We have a 1.7-inch cube. This was used by Robert Du Bois. And we have littler cubes that were used by Dan Wolfman, who started this lab here, and Jeff Amy. And the difference between these cubes is just changes in technology. That's effectively what allowed us to start sampling smaller materials. Archaeomagnetism and the way that we have to define sites is different than archaeology, because all of our databases are made for paleomagnetists that study rocks. So if I accidentally use a word without defining it, I apologize. This is my attempt to rectify that. So we have an archaeomagnetic site, which is a single heating event. That is the definition from paleomagnetism. A single heating event could be a lava flow. That is massive and covers a lot of different areas. In archaeomagnetism, a single heating event is a single fire in a fire pit. It's much smaller than a lava flow. Specimens are the single collected cubes from those sites that have those reference corners marked on them. And we have 51,000 of those. One of these cubes is a specimen. So you'll often hear me call them specimen cubes or cubes for that reason. In paleomagnetism, if I am studying a lava flow that is expansive and could cover, in some cases, multiple states or counties, it's very important to know where I took those samples from. That's the location. Here in archaeology, it's just the archaeological site. So if I'm collecting from a fire pit in Aztec ruin, then the archaeological site would be Aztec ruin. The fire pit would have a specific feature number within a specific room. So what does all of this actually look like when we put it all together? Well, we have to go back in time. So I said that these data sets turned 60 this month. It is because of this fellow, Robert Du Bois, and yes, I am pronouncing that correctly. He loved to go by Robert Du Bois, and he would correct everyone if they tried to pronounce it in the true French way. So first off, Robert Du Bois. He started this program, and he was originally at U of A, and in 1969, he moved to the University of Oklahoma. There, he developed a lab and trained many students. We have a lot of their theses in our lab, in our library. And some of those students went on to train additional students. So he went on to train Dan Wolfman in the early 70s, who started this lab in the late 80s, early 90s, and Jeff Amy. Jeff Amy and Dan Wolfman were not concurrent students of Du Bois, but then they did work together on a very few projects later on. All three of these scientists had their own interests and their own perspectives and their own personalities. And all three of them hardly ever worked together. So we have three separate databases. We have Robert Du Bois' database. We have Daniel Wolfman's database, who was carried on by Jeff Cox. So here's a picture of Jeff before he had long gray hair and before he retired. And then Jeff Amy trained Stacy Lingell. And these are three databases. When I started this project, we had wildly separate databases, wildly separate mathematical models to make a BGP curve. Nobody talked to each other at all. Some folks were had already passed away, and other folks did not want to communicate. So it was very siloed, and it was starting to cause problems. Specifically, if you look at this curve from the 1100s to the 1400s, and all four of these models, they're at least kind of all going towards Alaska, but they look wildly different.
Yeah.
And for the most part, these curves were only used for archaeomagnetic dating. They were not used for any other purpose. And so you would get 4 different dates off the same fire pit in this time period. And this was really starting to cause problems, especially in parts of southern Arizona. Because the curve, and these are 2 curves that you can see here, in this top one, or in this one off to the left, 1100 is to the west of 1300. Then that switched in the upgrade of that. And so you can start to get dates where the same data point was originally labeled as 1100, and then with the upgrade, now it's 1300, and which one's more correct? And it was really starting to cause problems. And that's where I came in. I said, well, this is silly. Why do we have 3 different databases and folks that don't talk to each other when 2 of them are dead? So we actually started to work with the previous director here, because he happened to have helped rescue a lot of these data sets. And they had not really been touched, because trying to manage the data sets for just over 50,000 specimens is insane. So we worked with him, and I worked with a team of undergrads, a team of volunteers, and over 7 years, we digitized these data. The main kind of fundamental reason behind this is, and the 60s, 70s, and even into the 80s, the interpretation of data was king. That was the thing you were publishing, and that was what was being quoted. Now, the specimen is the authority. And so if you look back at these old data sets and these old publications, you get beautiful interpretations. Some of them still hold today, but you have no idea what data went into that interpretation. Now, we want the data set so that anyone can interpret it. And as math changes, as computing changes, you can actually do these experiments again mathematically and using models, but you have to have the data to do that. All of the data that we had, for the most part, was locked up in paper records. Not possible. In 2016, this paper came out. It was an international group of scientists that worked together to basically address this issue that I'm talking about. How do we start to put limitations and kind of boundaries and goals in place for preserving specimen data? They came up with the acronym FAIR. In 2021, this actually got updated to FAIR-ICON, and I served on that paper for the ICON publication. But effectively, it's the same thing. So FAIR stands for findable, accessible, interoperable, and reusable. And basically, that means it's not findable if it's in paper records. It's not accessible if it's in paper records, cannot be used by anybody else or in a team if it's in paper records. But when they were talking about this, they used the word digital. So I don't really need to read this quote, but basically it's the idea that data should have long-term care as part of any proposal that comes out and as part of the thinking of this. This is not uncommon in archaeology. This is why we have an entire half of our building dedicated to storing archaeological research collections. But this is a new-ish thing in geology. But they use the word digital here, and this was a big oversight. And this was actually why in 2021, this got updated. A lot of our data, climate data, magnetic data, those are two easy ones, are locked in paper records. So this needed to be expanded to include not just digital assets, but paper assets as well. Unfortunately, funding institutions have still not really caught up to this. And the conversion of paper records to digital records is a massive expense because labor is so expensive. And they're still working on how to fund these kind of projects. My project for my thesis was funded by private donations completely. And to be honest, it still is. So why is this important? A lot of the data and specimens were collected using public funds, whether that's state or federal funds, whether that was funneled through a university or an office like our own. Almost all of the data was collected using some sort of taxpayer money, yet it is not accessible to any taxpayer today or scientist. They form the foundation of these modern studies. All of those interpretations from the 80s, things like that, are included in our understanding of Earth's magnetic field. But again, we cannot reproduce them because the data is not accessible. Access to sites, especially in archaeomagnetism, this is a huge one, have changed through time. Due to a whole bunch of politics, archaeology is inherently destructive. A site can quite literally get bulldozed or paved over. And modern construction is continuously destroying sites and overlaying sites with asphalt, for example. But what's the benefit of using archaeomagnetic samples? And that's the biggest one here. Archaeomagnetic samples, because they are tied to archaeological sites, and especially here in the Southwest, our chronology is often more precise and more accurate than rocks. And so if you want really high quality data and you want thousands of little photographs of what Earth's magnetic field looked like in the past, you have to have really good chronology. And archaeomagnetism can step into that role in a way that paleomagnetism cannot. So this was the general idea. I scanned data. I digitized that data with a massive team of help. I tried to format the 12 formats of data, and I only actually just understood what the 12th format of data actually was telling me like 2 weeks ago. And then we analyzed the data. So this is the most common data from the 70s. These are handwritten records that were coming off of a spinner magnetometer, one that Mark Slack, who was in the room, is very familiar with as he's helping us rebuild it. Here's another form. This is the one that we had no idea how to interpret. We knew that it was an astatic magnetometer. We just had no clue how to actually make the math work. I met with one of the lab techs from the early 70s that worked in Robert Du Bois's lab about 2 weeks ago, and he is finally able to help us unravel what this black box was. So we still have a little bit more work to digitize these because we had to not digitize them when I was doing this 5 years ago. We also had IBM printouts of data. This was all data done with punch card programs and punch card specimen data entering those programs at computing centers. So this was a massive undertaking. Those specimen cards do not exist. And if they did, it would be 70,000 cards of data that went into producing the 24 boxes of binders of data that look like this. We did get some digital data, which was amazing. We got 2 formats of digital data. This is the format that was used by Daniel Wolfman and Jeff Cox. However, they came in 2 different documents, and we had to get them to talk. We also got 2,000 pages of data that looked like this in a Word document with typos all through it. And we actually had to do a character recognition and character counting software development to actually make this do anything useful. And we're still working on making sure that we can fix all of the data sets. So in total, we expected to have about 1,000 samples and data sets from Robert Du Bois' estate. We had just under 2,000. And 42,000 measurements that we had to hand type up every single one of those. For Daniel Wolfman's collection, we expected about 1,000 sites. We got about 1,000 sites. And that was 37,000 measurements. About half of that was digital. And we had to type up the other half. In the Amy Lingell collection, both of them are still alive. We expected a couple hundred sites. We had 2,600 of them and over 100,000 measurements. Fortunately, those came digitally, but in that weird digital Word document. And so it took a little bit to format it. When we combined the data set, we ended up with 51,000 cubes from 1,200 different archaeological sites, from 5,700 different archaeological features, which are the fire pits. And you can see the % increase for the data sets that we have added to these databases worldwide. North America, obviously, that's where most of these scientists were based, had the most massive jump, going from 484 to almost 5,000, and that was a huge jump. So what does that actually mean? Because great, I can give you counts all day long. I have plenty of counts. But that's not incredibly useful. So if we take the data and we filter the data for what we defined as good data, that means good magnetic properties along the y-axis and good age control along the x-axis. What you see here is 286 data points. And these are the good data. This is not the great data. If we filter it for great data, that is the difference between the open symbols and the closed symbols. We then took some mathematical regression lines and statistical analyses, and we tried a whole bunch. What you see on the screen is the best fit polynomial. If you know anything about statistics, not the most ideal way of approaching this. But we are working with some teams today, and we are trying to apply transdimensional Bayesian analysis to these data sets so that we can actually look at how Earth's magnetic field is changing, not just in a small region, where we have to cap that region at a radius of 750 kilometers, but at a continent scale. So this is an active area of spiffy scientific poaching of statistical techniques, and they're still actively working on it. This is a team out of UCSD and a team out of Liverpool that are working on this behind the scenes. Don't ask me how to do it. I specifically avoid trying to do geomagnetic modeling because I am not an expert in it. And it's better to have the experts do this. So what we're looking at is the declination. So that's the angle this direction, and the inclination, which is the angle in this direction, and how that changes through time. When we pair these together, we get a VGP. So here are the 4 VGPs that had been published and used in the past for archaeomagnetic dating. And here is a color-coded updated version. The only time we have ever used this for dating is only about 8 months ago, and it was a sample that was dating in 1800s, and so we used this part of the curve down here. And that's because the rest of these curves, especially in the most recent time, do not match with the magnetic observatories for these two, so they can kind of not be applied to the last century. And Robert Du Bois's hand-drawn map based on hand-plotted data is actually the most accurate of the 4 models that was used in the past. And you can see it's similar to what the mathematical approach that we use today is looking like. So that was a project that we did in Placitas about 8 months ago, and we were able to use this new curve for the first time for dating, and it plotted right around in this area. Because this caps at 1850, or 1840, we were not able to really give a precise date, but that was all they needed, because they have historical documentation of the abandonment of that burned kiln site for lime processing from the sandias into concrete. And so they didn't need anything more precise than what we were already giving them. Yes.
On the map on the right, the lines, the points are way away from the line.
This is,
What causes it?
yeah, so this is part of an artifact of the mathematics that go into converting declination and inclination to Earth's VGP models. The other thing is that the line is the center point. And so if you have data over here and data way over here, it's going to try to kind of plot between them. So how we actually did this was we made our models in declination and inclination space, because this is 2-dimensional and way easier. And then we converted the green line to look like this. So we did not do this in VGP space, which is what Robert Du Bois had done. He had plotted it in VGP space, and then he took his pencil and drew a line through it, and visually averaged it. We mathematically averaged it and then converted it. The limitation with this plotting program is that you cannot plot the uncertainty bounds on the VGP map. And this is a massive limitation. And if we had those bounds, then it would be much more kind of obvious that the data are within the cloud of those uncertainty bounds. But we can't do that. It just doesn't work. We've tried, and it's unfortunately, these bounds are coming in as photos almost, and you can't convert the photo because there's no mathematical data behind it that we can convert. So there's a lot of limitations to these data sets. The original measurement techniques are very, very amazing at the time. That has changed.
Can I back you up?
Yeah.
On your two-dimensional inclination vector, I think you said you used 271 points.
286, yeah.
Okay. And how many do you have? 50,000 or something?
The data set here would be plotting from a pool of 5,700, because each data point represents one fire pit here. So we have 51,000 specimens that get averaged by their fire pit, and they get averaged together. And then those fire pits get plotted as one dot.
I guess one of the things I'm trying to figure out is what fraction of the data is ignored.
Right now, this is 286 of 5,700. So a lot is ignored, partially because we have to use a regional radius of 750 kilometers. So if I'm modeling in New Mexico
yeah.
and the data is from
Oh,
New York,
yeah.
which I have data from New York, I have data from Mesoamerica, South America, East Africa, or West Africa, and Southern Africa.
Yeah.
Can't use it.
Nice. Oh.
I also
Oh.
want good quality data. So if the age control is anytime in the last 500 years, that's not helpful. So those data were thrown out as well. They had to have an age bound that was less than 100 years. I did end up kind of throwing that out at one point and realizing that I needed to have more data in order to get a better model. And so you can see that there are really large age bounds on some of these data points, especially in about over 1,000 years ago. So I had at 1,000 to present, I capped it at, I think it was 100 plus or minus 100 years. So 200 years. And then previous to that, I had to increase that cap. And I can't remember what I increased it to make sure I had enough data to actually make a model work. And then in the XY direction, if I only had a fire pit that had 2 specimens, that's not a statistically significant value. And so those were thrown out. I used a limit that each fire pit had to have 3 data points. And that was the biggest limitation, which is this first line here. 3 separate cubes from the fire pit had to be used in the average of the fire pit. And that was the biggest change. So in the 80s, this changed. In the 80s, scientists around the world, archaeomagnetists and paleomagnetists, started collecting about 10 specimens per site, whether it's a lava flow or magma chamber, so a granite or an archaeomagnetic site. That was kind of always the case, but starting in the 80s, they started measuring all of them. Prior to that, they'd only select 1, 2, maybe 3 to measure it because the measurements took so long that it was so time consuming, they just couldn't do it. So that changed. So in the 80s, the techniques changed. This is why preserving these samples is so important, because we can go back and measure them now. We still have them. We can start to improve the numbers that we have because we can go back and start to measure these data sets again and these specimens again that I originally had to throw out of the data set because an N of 2 was measured. Magnetometers were not usually calibrated in the past. And so there's a problem with that because if you're trying to compare data sets, you have to know if your magnetometers actually talk to each other and have produced data that is the same. I think visually we can see that the data do actually plot very nicely together. They're all on top of each other.
Yeah.
But right now we have no way of mathematically showing that the data are actually cross-compatible. Again, these scientists did not talk to each other. So let alone share data or go to the one site and collect 16 samples and measure some at both labs. This was not a thing. So we're kind of having to do this in like retrospect. We know that at least 6 different instruments were used to collect the data in this data set. Some of our sites have limited archaeological context. For example, I have many sites that say 8 miles outside of Santa Fe. Helpful. So without additional information, we cannot improve the chronological estimates. And that's a very time-consuming process to start to try to trace some of those information. The temperature histories of the samples are rarely known. This is a thing in Paleomag 2. Was the fire pit used 100 times? Was it used 1 time? We don't really know. In some cases, this can massively affect the data, and in other cases, it doesn't matter. But we have no clue what the temperature histories of the samples are. And in many cases, we don't know what temperature the fire pits were even heated to. If they're heated to 200 Celsius, which is double boiling, we're good. but sometimes a fire pit will not get to that temperature. And sometimes a kiln can get to 1200 Celsius. So it just kind of depends. Archive specimen cubes are generally too large for the modern paleomagnetic equipment. And this is where Mark Slack comes in, who is probably playing with the system right now. All of our systems that we have now and have access to now in this lab can only measure 1-inch cubes. Those are the smaller cubes of that original photo I showed. We have 15,000 1.7-inch cubes. And the majority of these cubes can be used for additional study if we had a magnetometer that can be used. They do exist. Almost all of them, pretty much every single one that I have ever seen, requires liquid helium. That is also required by Los Alamos, and we are chopped liver. So we have to find another way. So we have a spinner magnetometer that is from 1967. It was built with vacuum tubes and analog systems. It was peed on by rats. It was corroded. Was disgusting. And Mark and a team of volunteers have been working to upgrade that system to a circuit system that connects with a laptop. So we are in the process of figuring out how to purchase the upgraded motor that is not bent so that we can actually use the system again. And then comes the fun part of making the system talk to the laptop, which is software.
You can't just cut the 1.7-inch down to 1 inch and use it.
That was tried. Jeff Cox did try that, and it becomes really difficult because you have to preserve the field orientation. And some of the samples themselves are bigger than 1 square inch because they're within a 1.7-inch cube. And so it just became a real headache, and it was deemed better, and I agree with this, to just fix the equipment and work that way. Even in our modern systems, the 1-inch cubes are not the standard internationally, so we have to retrofit sample holders, but that's simple because with 3D printers, you just say go.
You talk about 3.
Yeah, the chronological estimates. So this is a big problem with sites that the reports came out a long time after the samples were collected. So for example, you could collect a site and I'm going to make up numbers in the 80s. Dan Wolfman and Robert Du Bois passed away for some of these sites before the publication actually came out. And so we don't have archaeological reports paired with the archaeomagnetic samples. And so a lot of the dates that we do have are when they're in the field saying, hey, archaeologists, how old do you think this might be? Sometimes they're pretty accurate, especially if a site has a ton of pre-existing research on it and dendrochronology or really good architectural kind of typologies, which is not the right word. Thatcher and John can correct me there. But sometimes this is not the case, where it's a site that has very little other types of chronology that can be used. And so we just don't know. But now with upgrades in radiocarbon dating and better just data collection in general, because that has changed through time, some of these reports will be very helpful in improving the age estimates for the samples that we have, where we can start to get 500-year estimates potentially down to 200-year estimates. And with transdimensional Bayesian statistics, that's perfect. That's all we need for some of these sites.
So go with a radiocarbon date that someone 50 years ago thought was ideal, and now calibrating it stretches it out.
Exactly. Yeah, so there's just a lot of hiccups with the chronology. That said, because we have so much data, it worked. This is kind of the benefit of having a lot of data. You can get around some of these very minute problems.
Did you repair the luminescence?
We did not recalibrate any ages, because trying to do that for 5,700 sites, or archaeological features will be the rest of my lifetime. So we have not done that. The big thing here was just getting the magnetic data that we had and the field data that we had digital.
How many 1-inch cubes?
That's a good question. So I can tell you exactly how many 1.7-inch cubes we have because we just finished about a month and a half ago organizing those
Yeah.
and putting them into a digital database. 1-inch cubes, that's a little bit more difficult only because we just recently in November acquired Stacy Lingel's collection, which includes Jeff Amy's collection, and we have no idea how many are in there. We have not counted them yet, but I can tell you there are 20 boxes of them. And those are Banker's boxes of
It's a
1-inch
foot size,
cubes,
yeah.
so there's a lot. My estimate is we probably have 35,000 of those 51,000 specimens left. We do know, and that was confirmed, that at one point Jeff Amy had to throw a bunch out due to some requirement of the university that was working at the time. And we also know that some have been lost through time or they're stored at other agencies. So future goals is to develop additional reference curves using very novel techniques. These are these transdimensional Bayesian statistics that I keep mentioning. And the idea would be to eventually incorporate magnetic intensity, which is looking at the field strength instead of just the direction. We've kind of re-subdivided the United States into different regions. So we have the Four Corners curve. Yes, archaeologically, Four Corners is a very small area compared to what we are defining as a 750-kilometer radius, but it is what it is. So the Four Corners curve incorporates Utah, Colorado, Arizona, and New Mexico because it's a circle that also allowed us to get down into Chihuahua. We also have the lower Mississippi River. This was previously called the Southeast US curve, yet it was Arkansas. This is confusing to international audiences. They do not understand the colloquial language that we use here to define some of these regions. So it will be changing to lower Mississippi River because that is international.
Right.
I don't think anyone in their right mind internationally would call Arkansas Southeast US. We'd love to develop a web-based platform that allows archaeologists to update previously reported archaeomagnetic dates and reassess those dates with their regional chronologies. Again, this goes back to Southern Arizona, where this is a massive problem. We want to further refine and update the sample metadata and the independent chronologies. That's going back to your question, Bill, and your question about, well, let's just like redo the dates. Yeah, that'll be a 30-year project. Obviously, we'll bite the elephant in small bits, but that's a massive project. And then identify time periods with low sample density, both in direction and intensity. And when opportunities become available to collect data from that time period, then we need to take those opportunities. And then for the samples that we can and where it's appropriate and possible to demagnetize, we would love to continue to do those demagnetization experiments in-house. We have the ability to do that with the 1-inch cubes, and we're working on the 1.7-inch cubes right now.
What information is that given?
Since a lot of these cubes, especially the 1.7-inch cubes, were never actually studied, they were measured once, which is effectively like taking a measurement, like it's your starting measurement, it's your control. They've never had any experimental treatment. They've never experienced that at all. And so we can continue to demagnetize them. We can continue to use those for active experiments. And they are perfectly viable as if we had collected them yesterday. And so that's a huge win. This is effectively a sample library that can continue to serve as the basis for my own research, this office's research, continued international goals, but it can also, and hopefully will include graduate students so that we can move this process along a little bit faster. And there are plenty of master's, PhDs, and undergrad theses in these data sets. So that's it. there's not too many of us here, and most of you have already seen the lab, but for those of you that haven't seen the lab, it is in boxes right now as we're working to make a sample archive for all of these 51,000 data. But you're welcome to come see boxes. I will gladly show you boxes. And if you'd love to help me move boxes around, that would be fantastic too. So, yeah.
I have a question.